So in the last video I mentioned a brain wallet, and I'm not a big fan of brain wallets, and that's because they're dangerous and they're not a good idea. And if you don't want to watch the rest of the video, just your key takeaway is don't use brain wallets. And I'm going to tell you exactly why and why that is, but the key takeaway, the short version, just don't do it. So having said that, the thought of a brain wallet is pretty cool. So the whole idea is that with just you can store the cryptographic keys needed to spend or unlock your Bitcoin purely in your brain. So you can memorize everything you need, and it's essentially like holding Bitcoin in your brain. And that's pretty cool. It's a very cool idea, and makes you wonder. You know, there's those laws about moving money across international borders. You can't move more than 10,000 cash across an international border. But if they're in your brain, what does that mean? Can they? Is that illegal? If you know the keys to unlock Bitcoin that works across the world, and you step over one border, if you go to Mexico or across, go on a vacation to Europe, what does that mean? So interesting legal implications of that. So while it is cool, and I will say that there is one safe way to do a brain wallet. And you'll have to keep watching to understand why that is. But there is one safe way, but you have to have Mensa level memory capability. And we'll talk exactly how to do that. If you don't believe me, keep watching. So to first describe, to get into the details of why brain wallets are a bad idea, let's first talk about just basic password storage and how websites store passwords. And eventually we'll talk about how the blockchain wallet stores passwords, and then talk about the differences in the blockchain wallet. And then we'll be able to compare what is the current standard for good password management, and use that to evaluate how bad of an idea brain wallets are. So just a general password storage for a website, for instance, or a Linux server or a Windows server. You have your password, and you run it through a hash function, and you get this resulting output. This resulting output, the properties of a hash function is that it's one way. There's no mathematical operations that you can take this output and derive this input. So that was the first Unix boxes and everything used this technique to, when users typed in the passwords, it would store it, and it would store this resulting hash. And why that's good is, let's say a hacker was able to get onto that server. If they were able to read the database and see, they were able to get the resulting hash for all the individual users on that server, having this hash does not let them get the password. However, back in the 90s, I read a book called The Cuckoo's Egg, and it talks about a Unix admin that was seeing hackers get into a system and they pulled this password database. He's like, well, that shouldn't give them anything, because it's a one-way function. There's no way to reverse that. But given a little more thought, he realized, well, users don't always pick good passwords. So what the hackers are doing is they get the list, the resulting hashes for all the users on a particular server. They just guess passwords. So they just put in ABC123 monkey. They just guess all these passwords, and then they can compare the output of that with the database they had, and then they could get the username and password for all the users on that box. And that method is called brute force, or it's just called brute force password hacking. So the next step for the server guys was to implement what's called a salt. So what that means is the server would generate a salt. Originally, I think it was just a per server salt, but now the current best practice is for every single user, the server side on the server will generate a unique value. And then that will be added to the password. And this happens transparent to the user. The user just puts in its password, and then the computer or the server adds a salt, and then the hash of all of that is taken to get a resulting output from that hash function. And what that means is now if a hacker has a password database, each one of these has each one of them has its own salt. So while before you could grab a whole password database and you'd try hash of monkey, you could compare the output of that hash to the entire database to see if any user had that match. But now what you have to do, because each user has a salt, you have to run so you have what's called a dictionary, the hackers do, of passwords that they think users might try. So now they have to run their dictionary and do a hash and add the per salt to each one of those, and they have to do it on a per user individual basis. So all that means is it makes it harder for the hacker to take a password database with resulting hashes, convert that into user and actual passwords. So to bring us up to modern day password management from a website or server point of view, these are individual hash functions, and MD5 was the first one, which is first one that was done. Is no longer secure anymore. We moved to SHA or SHA-1, then SHA-256, and then so SHA-256 is a very good secure hashing algorithm. However, it can be done very quickly. So, and there's hardware implementations of SHA-256, so that hackers can do this very, very quickly. bcrypt and scrypt take the same functionality of this particular one, but they use a lot of memory and take much longer time frame to do. So that means if a hacker wants to try basically guess a user's password 10,000 times, if this hash function was used scrypt, it's going to take a lot longer than if they'd use SHA-1. And then this most state-of-the-art password management today is what's called this PBKDF2, which is password-based key derivation function version 2. And what that does is that allows you to use one of these other hash functions, but do it more than one time. So you hash the hash. And all that does is it means that a hacker now, the number of iterations you do in PBKDF directly impacts how many passwords that the user can do or the hacker can do in the same period of time. So if you do 10,000 iterations or 20,000 iterations of one of these hash functions, then the attacker's essentially, if they want to try the same number of passwords against your particular user because it's salted, it's going to cost them 20,000 times the cost and time and labor and power and computing power to do that. So, having said that, let's put this in perspective. LinkedIn, their password database was hacked. That was like a year ago, and they were doing SHA-1, no salt at all. So that's why very quickly a lot of the users in that database, their passwords were just revealed. So it's a very bad situation for LinkedIn, and they were chastised by not using the state-of-the-art PBKDF2 with a per user salt. So let's talk about even though we're talking about doing all this functionality, let's keep in mind that the hash or your salt, let's say you have a password, it's salted, you're using the best crypto, it's going to result in this resulting hash. Now typically, this, like for LinkedIn, this is what logged you into the website. But for Bitcoin, what we're actually doing with this password, let's say your password is monkey. So that's not a very good password, but if you type that into, use that as your Bitcoin password for your wallet that's on your computer, it's actually behind the scenes automatically generating a very good cryptographic password for you. But it's hiding, and it's actually using encryption and using your weak password of monkey. It's using the output of your weak password to encrypt your wallet locally on your laptop or desktop that contains the good key. Because we all know monkey's not a good password. And the resulting output, even using PBKTF2, the resulting output of this hash is not going to be good and safe because the input is just so bad that the state-of-the-art password still doesn't really help you a whole lot. But so to protect you from that, this is like a file on your laptop, and this file is encrypted itself with the bad password. But when you type in your bad password, it unlocks this, gives us access to this good password. And your Bitcoins are actually secured with this good password. And what this is actually a 21-character, completely random, using upper lowercase numbers and symbols. And this is about the equivalent of 128 bits of entropy of protection. So this is what you need to actually hold Bitcoin securely, is this level of security. So then let's say you want to spend Bitcoin. It uses this private key, this cryptographically good key, and generates a public key. And again, this private to public key translation is also a one-way function. There's no way to go from the public key to the private key because that would kind of defeat the whole purpose of public-private key crypto. And then this public key is broadcasted out onto the blockchain. So everyone can see, when you send money with Bitcoin, everyone sees your public key, and that's actually how they verify that you are the owner of that Bitcoin, is that what goes out on the network is actually your public key plus a transaction signed with your private key. So the details, if you want to know more, it's probably a different, you can look up how the underlying crypto works with Bitcoin. But that's not the whole point of this video. The point is to look at, this level of security is what you need if you were going to broadcast. Again, there's no way to reverse this, but you can guess. You could try to guess this. But this has so many bits of entropy, so many random characters. No, it's impossible for anyone to guess, to randomly try passwords. Just to count, for a computer to count from 1 to a number with 256 bits, which is like 1 times 10 to the 77. The minimum amount of entropy needed to flip a bit by the laws of thermodynamics, you would need more energy that's in the sun to just count from 1 to the number of possibilities that we're talking about in these numbers. So it's very secure. So now, what a brain wallet is doing, a lot of these brain wallets on the web, like brainwallet.org, Bitaddress, those are the two I know off the top of my head. They are actually, a lot of them, some of them use SHA-1, some of them use SHA-256. Actually, I'm not sure. I think actually all of them are using SHA. Let me just double check. So the brain wallet websites are using a single SHA-256 of your password and generating, they're bypassing this whole intermediate step where the computer generates a secure password, and it's taking this output directly and putting this out on the the block, or it's not taking the private key and putting it out the blockchain, but it's using the output of your password directly as the public key. Whereas in this scenario, the password's only unlocking this file that's got the really good private key. Now we're using this directly as a private key. This actually, I'm going to draw that. So this goes to a public key. And then that public key is broadcasted out onto the network anytime a transaction is done. So what this means is hackers that see the blockchain, so they can see this public key, so they can try passwords all day long, months and months, and see every transaction, every public key out on the blockchain network, and see if they hit your password. They can do the forward operation and compare it to every public key that they've ever seen out on the network. And if they get a match, they now know your private key and can spend your Bitcoin. So that's why the we call LinkedIn, or anyone who does not use the state-of-the-art password derivation functionality, they publicly get chastised by the security community of not following those best practices. But yeah, here we're essentially this would be like LinkedIn broadcasting their password database all the time, because they were just doing a single shade. They were doing shade 1, but the Brainwallets are doing shade 2 physics, so marginally better. But then they're essentially taking the result and broadcasting it out on the network. It is going through kind of one other private to public key step there, but it's the same idea. So we yell at LinkedIn for being dumb, but that's essentially what Brainwallet is doing, is that level of breach. So immediately, LinkedIn says, change all your passwords because you're at risk. But yet, Brainwallets are broadcasting their public key out on the network. Now, having said that, I guess I said there's one way to do it correctly and keep it safe. Now, is for your input password to be absolutely as secure as this password that would be generated by a computer. And there is exactly one way to do that, and that is to have a computer generate you a password with 128 bits, with a minimum of 128 bits of entropy. I actually prefer going higher, using 256 bits of entropy for my password inputs, just to be on the safe side, but 128 bits is kind of the standard in the Bitcoin world. And for your password, level of password entropy. So you can actually represent, this has that level of entropy right here, but this would be essentially impossible to memorize, in my opinion. Maybe you guys are having a little Mensa card, like, oh yeah, no problem. But for me, this would be impossible. And actually, there's a better way, with a string of just random words. This whole block of words has the same level of entropy as this. So it's a lot more characters, but this is a lot more memorizable. You're a lot more likely to be able to memorize this. So if you can memorize this, you can do a Brainwallet. Just don't ever forget it, because if you forget it, it's gone. So I'll show you. Some. I'll mention this here. So if you think you can come up with a password by yourself that's secure, you're wrong, because any trick that you can come up with, hackers can think up as well. This is a password that Ars Technica did an article on password hacking, and they hired real password hackers and gave them a database. This was a password that was cracked in just a couple of hours by one cracker, and that's using very minimal amount of gear and effort. So if your password, that looks like a pretty darn good password to me. I would look at that and be like, oh yeah, that's pretty darn good. But no, it's not. The only way to keep your Bitcoin safe is basically just don't use a Brainwallet, or if you do, use a computer to generate random words safely, and then memorize that. That's the only way to do it. Or do the same process offline with like some dice or something along those lines. So here's an example. We'll type in just that password, ABC123. So we're at Brainwallets website. So I type in ABC123 as a passphrase, and it's going to give me a private key and then generate a public key address. I'm going to take this public key, copy it, and go over to a blockchain explorer, and I search for this public key. And let's see if we find anything. So ABC123, no transactions. So no one has actually, that we're aware of, has used that transfer. So let's try, actually there is an awful one called Bitcoin is awesome. So that generates this public key. We copy and paste. Let's put this. And there's transactions on this account. And not only are there transactions, but there's 501 Bitcoins. You've got to be kidding me. Someone transferred 500 Bitcoins right here on November 20th, 2012 into the address secured by that password Bitcoin is awesome. And you'll notice, if you look at the time frame, it is 11:20. 1 minute after it was transferred in, it was transferred out. My guess is there's bots set up to look for addresses that are known, and the instant money's put in, it transfers them out. And let's see, the input was 1 TM, and the output was, actually it was the same input and output. So this person actually probably got their money in and out in 1 minute. I don't know why anyone would do that, but they did. But if you look some of these other cases, we've got 1042, 30 seconds later, it is not going back. This 14G2 is not one of the inputs, so that money is definitely gone. So that there's, this is just one example. Actually, I've got the NXT. Let's close this. The NXT wallet. I happen to know that ABC123 does work, so I typed in ABC123. I hit log in, and account balance. See that someone transferred money in. Luckily, not a whole lot, but immediately after, money was transferred out. Unfortunately, the NXT allows you to type in any password there. The client does give you warning that your password is too short. But I really think NXT should not advertise Brainwallet as a feature. But that's just two exact examples of why Brainwallets are a bad idea. So, all right, thanks for watching, and I hope I prevented some people from losing some money. Take care.